All right, question 21. What happens to our confidence interval from question 20 if we raise the number of samples? Raising the number of samples is going to increase this number, 100. And so it's going to increase the square root of n, but it's in the bottom of a fraction, so it decreases the width of the confidence interval. Okay? So that's going to decrease. Raising the number of samples should shrink the confidence interval, gets narrower or more accurate, which makes good sense. Also, what happens if we lower the percentage for the confidence interval from 95% to 90%? Well, if you lower the percentage, you're less confident in your interval, and that means that your interval must have been narrower, right, rather than wider. So I think the answer here is 2. Raising the number of samples makes the confidence interval narrower, and lowering the percentage also makes the confidence interval narrower. That would be the effect. Okay, question 22. U.S. Navy planes have been launched to protect Allied forces in Libya from Russian mercenaries. 20 targets are selected, and there's a 90% chance that each target is destroyed. The results for each target are independent of the results of the other targets. We believe the Libyan troops can deal with the mercenaries if fewer than 4 of the targets survive. Set all prob equal to the probability that all the targets are destroyed. This is a binomial probability. And if I want all of them to be destroyed, I want the probability mass function at 20. I want 20 targets to all be destroyed. There's 20 targets in total that could be destroyed. So I'm performing coin flips where the coin flips have a 90% probability of coming up heads, of destroying the targets, right? And I want all 20 targets to be destroyed. Set few prob equal to the probability that 4 or fewer of the targets survive. A bit of a tricky thing. So CDF for a number or fewer, CDF of 4. There's still 20 missiles being fired, but this time, since I'm counting the number that survive, I want P to be 10%. That's the chance that a target survives, right? If 90% of the targets are destroyed. So 12% chance that all the targets are destroyed, 96% chance that fewer than 4 of the targets survive, right? Okay, the last question, I'll just run through kind of quickly, but it walks you through essentially a Bayes theorem calculation. So suppose that 40% of all cell phones in Annapolis are Android and the other 60% are iPhones. 20% of Android phones have a cracked screen and 30% of iPhones have a cracked screen. We randomly find a phone that has a cracked screen. What's the chance that it's an iPhone? Okay. So we're going to make an assumption here that there's 1,000 phones in Annapolis. This number doesn't really matter too much, but it will help us to do the calculations pretty easily. So just imagine there's 1,000 phones. And since 40% of them are Androids, then 400 of the 1,000 phones are Android and 600 are iPhones, right? And of the 400 Android phones, 20% have cracked screens. So there's 80 that have cracked screens. 20% of 400 is 80. Of the 600 iPhones, 30% have cracked screens. 30% of 600 is 180. So 180 have cracked screens. So how many cracked screen phones are there? Well, 80 plus 180 is 260 phones with cracked screens in Annapolis. So what's the probability that this phone with a cracked screen is an iPhone? Well, there's 180 phones that have cracked screens that are iPhones, and there's 260 phones that have cracked screens. So the number of phones that are iPhones that have a cracked screen divided by the number of phones that have a cracked screen is 69% or thereabouts. So the probability is 0.692, etc. And that's the answer. It's about a 69% chance that the phone is an iPhone. Okay, a bit more likely than if you just knew that it was a cell phone in Annapolis. That would then be 60% chance that it's an iPhone. Okay, that's the summary of our practice test answer.